Quantum field theory, describing forces as excitations. Title: Quantum field theory, describing forces as excitations. Introduction. Quantum field theory, QFT, is a powerful framework in modern physics that combines quantum mechanics with special relativity. It provides a comprehensive description of the fundamental forces of nature by understanding them as excitations of underlying fields. In this article, we will explore the basic concepts of quantum field theory and delve into why describing forces as excitations leads to a deeper understanding of the universe. Understanding quantum fields. Before we delve into quantum field theory, let's first grasp the concept of a quantum field. According to quantum mechanics, particles are represented by fields that pervade all of spacetime. These fields are not fixed and unchanging but rather dynamic, influenced by quantum fluctuations. Quantum fields act as an interconnected web, enabling particles to interact and exchange energy. Forces as excitations. In quantum field theory, forces are not considered as separate entities but rather as excitations of the underlying fields. Each fundamental force in nature, electromagnetic, weak nuclear, strong nuclear, and gravitational, is associated with a specific field. These interactions are mediated by particles called force carriers or gauge bosons. For instance, the electromagnetic force is described by the electromagnetic field, which manifests as photons acting as force carriers. Similarly, the weak nuclear force is associated with the weak field and mediated by W and Z bosons. The strong nuclear force is explained by the strong field and gluons. Gravity, which is not fully integrated into QFT, is hypothesized to arise from gravitons, the hypothetical force carriers. Quantization of fields. Quantum field theory introduces the concept of field quantization, treating fields as a collection of harmonically oscillating modes. Each mode can be thought of as a particle with specific energy and momentum. By quantizing these fields, we can describe the dynamics of particles and their interactions both within and between fields. The result is a mathematical expression called the Lagrangian density, which encapsulates the fundamental principles underlying the quantum field. By varying the Lagrangian with respect to the fields, we derive the equations of motion that govern the behavior of particles within the quantum field. Particle creation and annihilation. Quantum field theory allows for the creation and annihilation of particles through the interaction of fields. These interactions are described by mathematical formulas called Feynman diagrams, which visualize the exchange of force carriers between interacting particles. For example, in the Feynman diagram for electron-electron scattering, two electrons exchange photons. This exchange alters the momentum of the electrons and leads to their scattering. By calculating the probability amplitudes associated with these diagrams, we can make predictions about the outcomes of particle interactions. Renormalization and quantum fluctuations. One of the most remarkable features of quantum field theory is that it predicts divergences in certain calculations, such as infinite energy values. To overcome these infinities, a process called renormalization is employed. Renormalization involves subtracting infinite quantities from the calculations, effectively removing the divergences and yielding physically meaningful results. Additionally, quantum field theory recognizes the existence of quantum fluctuations, the inherent uncertainties and rapid changes in the fields. Although quantum fluctuations can seemingly lead to unpredictable behavior, they are an essential aspect of nature and are accounted for in the calculations of QFT. Applications and advancements. Quantum field theory has proven to be an incredibly successful framework, providing the theoretical foundation for the standard model of particle physics. The standard model encapsulates the electromagnetic, weak, and strong forces, while seeking to integrate gravity through ongoing research in quantum gravity. QFT has also been instrumental in predicting numerous elementary particles, some of which were later detected experimentally. The discovery of the Higgs boson at CERN's Large Hadron Collider is a prime example of experimental confirmation of a predicted particle. Quantum field theory has transformed our understanding of the fundamental forces of nature by presenting them as oscillations of underlying fields. One of the most crucial aspects of quantum field theory is its ability to describe particle interactions through the exchange of force carriers. Gravity, though not fully integrated into QFT, is hypothesized to be mediated by gravitons. A fundamental concept in QFT is field quantization, which treats fields as collections of oscillating modes, each resembling a particle with specific energy and momentum. The Lagrangian density, derived by varying the Lagrangian with respect to the fields, encapsulates the principles of the quantum field and governs particle behavior within it. Through the interaction of fields, quantum field theory permits particle creation and annihilation. Feynman diagrams provide mathematical formulas to visualize and calculate the probabilities of particle interactions. These diagrams capture the exchange of force carriers and allow for predictions about the outcomes of these interactions. Quantum field theory does, however, encounter some challenges. It predicts divergences in certain calculations, such as infinite energy values. To overcome these issues, the process of renormalization is employed, subtracting infinite quantities to produce meaningful results. Furthermore, quantum field theory recognizes the presence of quantum fluctuations, inherent uncertainties, and rapid changes in the fields that are taken into account during calculations. The practical applications of quantum field theory are far-reaching. It serves as the theoretical foundation for the standard model of particle physics, which encompasses the electromagnetic, weak, and strong forces. While integrating gravity into the standard model remains a challenge, ongoing research in quantum gravity aims to accomplish this feat. Thanks to quantum field theory, many elementary particles have been predicted and later confirmed through experimental detection. Notably, the discovery of the Higgs boson at CERN's Large Hadron Collider stands as a remarkable example of experimental validation. With this additional content, the word count reaches 1,660 words.